nanoHUB.org.
Online simulation, and more for nanotechnology.
So in this training, our aim is to also have hands-on training. So these are the links to the tools. We will actually first go through the image processing tool and Raman tool, and then we will move to Gr-ResQ, where we will use the submit tool and as well as the query tool. So you can probably open them now. The tools are currently being updated continuously with a lot more features and a lot more debugging issues. And since we hope that this would be a great platform for you to see how the tools work, and if you have any questions or if you have any suggestions, we would be very happy to have feedback from you. This is how nanoHUB looks like. And then the first thing that we're going to do is we are going to go to the SEM image processing tool. As soon as you open it, you can actually follow along with me while I'm doing this, so that you will also have hands-on training. And also the images were shared through a Google Drive before the probably on Monday. And if not, if you have your own images, that could work as well. You basically need any image which has which is in JPEG format or PNG format or a TIFF format. And you can then launch the tool. So this is the opening page of the tool. And we have three windows. This is where you will have layers for image analysis. And this is our working space. And this is our preview space. And we will have, you can first import an image by clicking on File, Import. And it will allow you to upload a file. And you can take, for example, this image and then click on Upload. And it will upload it. And so this is how the image currently looks like. And you can zoom in and zoom out using the plus or minus window, or you can use your mouse roller button as well. And if you want to fit the image to the window size, you can just click on this. And you can move the image using this hands tool. So you can just move it anywhere depending on how you want to see it. So the first thing that we're going to do is remove our scale from here. Because the scale will not be very helpful in actually identifying regions of graphene. So the first thing that we do is open this drop-down menu over here, and then click on Remove Scale, and then click on plus. So once we do that, it will automatically remove the scale that is there in the image. And then we can go ahead and use our first tool. So the main aim of this whole tool is to identify regions where graphene is present and where graphene is not present. So we can do this with using different methods. So the first method that we're going to study is color masking. Then we also have template matching, k-means, which is a clustering method. So the next thing that we're going to do is color masking. So we can, again, click on the drop-down menu and then select color mask, and then you can add. So over here, you can see that there are different intensities present over here. So it basically, what it does is it groups all the intensities that that are near each other, and then you can see these peaks. So what you have to do is you have to either select the lower ones or the higher ones, and then you can see that, oh, this looks like all the graphene regions have been actually identified. But the problem with color masking is that it does not exactly know where which pixel is graphene and which pixel is not. What it does is it just separates out the intensities. So it's not a very robust mechanism. And then there are a lot of issues, and this is very like you require a lot of human interaction to actually do this whole process. So instead, let us now remove this mask. So to remove a mask, you have to press the minus sign. And then let us go forward and do a filter pattern, which is we can filter the image using a template matching method. So what you have to do is then you have to again press the plus sign. So the tool works like this, that you can choose any of these layers, and then you have to either select the plus sign or minus sign to add it or delete it. And once you add the filter masking, it asks, you cannot exactly see the image over here right now. The reason is that you don't have any filter added over here. So over here, we're going to first select template matching, and then we are going to click on plus. And once that is done, you can see that it is, you can see this small red square over here. So what template matching does is that it finds the regions which are similar to the region highlighted by the square. So you can move this red square anywhere over the image, and then you can work with the threshold, and then it will automatically identify regions where there is graphene or where there is no graphene. So you can go like this or like this, and you can also do invert selection, where it will automatically negate all of the selection that was already there. As you can see, this is not a very great masking technique either, because it is not able to identify, again, differences between this region and this region. So you can actually use an erase tool, which is again over here you can click on erase tool and then click on plus, and then you can erase. But again, as you can see, this requires a lot of human interaction with the tool. And to minimize this, we can go forward and remove the template matching. And then let's work with k-means. So what k-means is, it is an unsupervised clustering method which takes all the pixels and then groups them based on similarity. So it automatically identifies regions which probably have graphene versus the regions that do not have graphene. So let us do that. And over here, you can see that there is a tab called window size, where you can enter your window size. It basically is the size for classification. And then you have clusters. So it is how many clusters of will be formed out of the pixels. So if you group the pixels, you would want to know, I want to know whether there is graphene or there is no graphene. So I'm just going to put it as 2, because I just want 2 clusters. And then there is stride length. So while doing the whole image analysis, it can skip pixels in between. So as of now, it is going to skip 3 pixels in between. The lesser the number, the slower the whole result will be, because it is going to actually study each pixel. And then what we can do is we can press run and run the code. And then once you select one of these, it is going to show you which region has graphene versus which does not have graphene. So what you see over here is what we call a mask. And you can always export this mask and save it to your file, to your computer. And this is one of the most one of the best techniques in this tool, where you can identify graphene with least human interaction. Our ultimate aim is actually to use machine learning models to do this automatically, where you will have to do nothing. You just have to upload an image, and then the model will itself tell you where graphene is present versus where graphene is not present. So once this is done, we can actually also do some alignment measurements. So for alignment measurements, what we have to do is we can save this filter. So let us just leave it there. And then we can add a canny edge detector. So what canny edge detector does is it identifies the edges of the image. So you can see that these are the edges of the image, and you can vary the threshold however you want, so that only edges are identified while the other regions are removed. And then what you have to do is you have to blur the image. This step is actually very important because the alignment mechanism works with the gradient of the intensities. So only if there is a gradient, it will be able to identify that, okay, this is an edge and this is where I have to align. And so what does the alignment? After this, we can do alignment and we can add that filter. What does alignment do? It basically identifies the regions where it basically talks about tells you what angles are present in this image. So for example, for this, in Gr-ResQ, the horizontal line is 90 degrees, so that you have almost a very high peak at 90. And then you must have another peak at this line and this line. So what you can see is that there are only 3 angles present in this whole image. And that is really good because this says that the whole grain, each grain is aligned very well to each other. So each graphene layer is actually very well aligned to each other, which we can obviously see as well. And you can also see that over here, where there is only one peak over here, this is a comb function, which basically uses all 3 angles to align them together. And you can also vary the size of the Sobel filter. So this whole process is done using Sobel filtering. And you can see that it becomes a lot more definitive. And this is how you can identify the orientations that are also present in the image. For example, if graphene was not oriented parallelly with respect to each other, then you would have many more peaks over here, and which would result in, which when grows into a bigger film would result in grain boundaries, and hence you would not have a single crystal later. So this is one method to actually tell you how good is the synthesis quality. Another thing that we also can get from this is fractional area. So when we did filter masking using k-means, it gave us a value of 0.347, which was actually the area covered by graphene. So this is another thing that we can get out of this tool. So this is mainly about our image analysis tool. And once you have generated the image that you like, you can always export it, you can save it. And as of now, we are also working on a machine learning model which automates all of this process so that you would not have to do a lot of such analysis by yourself. But the tool will automatically do it for you and present it to you. So this was our SEM image tool. You can upload any image that you like. It may not actually be an SEM image, but our main goal over here is to work with graphene scanning electron microscopy images and to identify regions of graphene versus regions that are not present, that do not have graphene. So yeah, so the question is, how are the grain boundaries of the metal catalyst impacting the tool detection for graphene domains? So the grain boundaries are actually not identified usually through the tool. The reason being, the grain boundaries do not give a very big contrast, versus graphene and the substrate has a large contrast. But if the grain boundaries have a very huge contrast, they can actually be identified separately. But usually another thing that the tool also does is finds edges, and with that feature, it will not identify the grain boundary to be graphene. I guess I can move to the Raman fitting tool. So the next is the Raman fitting tool, where the main aim of this tool is to fit a Raman spectrum, which says how which gives out how the quality of graphene is, and also talks about whether graphene is actually present or not. So in this tool, this is a very simple tool, as in there are not many buttons as of now. So this is the main opening page of the tool, and to upload a file, you can press on upload file and then choose a file. And then I think this file was also sent to you through Google Drive. And you can click on upload. And we have another question. What kinds of file types can be supported? This tool, as of now, currently just accepts text files. So you would have to save the Raman spectrum as a text file. The text file is basically, as of now, the text file that I've uploaded is a single spectrum. It has the intensity, it has the wave numbers as the first column, and then tab limited space. After a tab limited spacing, it has the intensity saved in the file. And then once you have uploaded the file, you can press on do fitting, and it will automatically fit the graphene spectrum. So this is how a normal graphene spectrum on copper looks like. So over here, you can see a D peak, a G peak, and also a G prime peak. And this is the fitting that has been done by the tool. What the tool does is it fits the whole spectrum to Lorentzian distributions and identifies the peaks and reports the parameters that it used to actually fit the spectrum. So over here, we can see that the ratio between the intensity of the G prime peak versus G peak is almost 2. And that basically means that this is a mono layer. And that is what the tool also reports, that the number of layers is mono layer. It also gives you the intensity value. So alpha over here represents the intensity. The gamma value is the full width at half maximum. And then the omega over here represents the position of the peak. All of these are very important parameters. The intensity helps you analyze how how many layers are there. How is the quality of graphene? Over here, there is another metric called quality metric, which relates the D peak and G peak and says how good is the quality. So as of now, since the D peak is a very high, is almost near the G peak, it says that the quality is about 0.5. And then it also reports the position of the peak, which is another important factor in Raman spectroscopy analysis, because the shifts in this peak position will show that the graphene has strain or does not have strain, or if it is doped, etc. So you can actually zoom into this how much ever you want, and in case you zoom in like me into the whole window, you can always press A, and it will get you back to the normal window position. And you can also see use overlay over here to see how the actual fitting is on top of the data that has the actual spectrum. So over here, you can see that this is the raw data, and you have the fitted data in red, and the test data, which is the data that has been stored, that it actually uses to fit the Lorentzian distribution. And over here, the diffs is actually another, just a representation that, okay, this is a mono layer. The lower the value of this delta, that means this is a mono layer. And as of now, the tool has just single spectrum, like it accepts only single spectrums, but we are moving, we also wish to incorporate map files into this so that we can actually enable better analysis of graphene over a large domain. And this is basically the Raman tool. Does the tool only use G dash to G ratio, or does it use any information from the Lorentzian? So the G dash value itself has been determined by the Lorentz fitting. So only after it fits the Lorentzian curve, it actually says that, okay, this is where the peak lies. And it usually normalizes the peak intensities, and that's why you see that the range is from 0 to 1. Is there a way to save this information? As of now, no. You cannot actually save this information right now, but we are working on this. Is actually in our next tool update that we will be able to download these these as images, and save the fitting parameters as well. To me, it looks like you have parasitic small peaks, and the tool wrongly took one of those as D peak. Also, what about the background? Yes. So yes, that is an issue with the current tool version, where it it just tries to find a D peak even though it is not present because of this background that is present in this due to copper actually as its substrate. To work with that, what we have done, what we are currently doing is we take a copper Raman peak without graphene, and then we subtract it from this actual graphene Raman spectrum, and then we do the whole analysis. So that helps us remove the background. The 2D to G ratio depends on the CU grain orientation or the substrate in general. The 2D to G ratio does not exactly depend on the grain orientation of copper. And usually the grain orientation, the impact of the grain orientation on the graphene peaks is not very high. So we haven't actually faced any issues as such, but I think we would have to look into this a little more. I don't really have a direct answer to this. How does the tool identify the D peak from the raw data? Yes, as I told, usually if you have a very high D peak, usually the background is not this high, and you would, if there is a lot of defects, you would have a very prominent D peak. As of now, since the D peak is lost in the substrate background, it uses the substrate background to determine this D peak, which is not the correct way of currently determining this. Yes. It keeps giving the error server disconnected. It is possible that nanoHUB is not able to currently take a lot of people working on the same tool at the same time. So this might happen. I would suggest you try again because usually it refreshes every single time. So it should be fine the next time. How does it detect bilayers versus trilayers if it is AB stacked or twisted? Again, bilayer and trilayers, it would basically what it does is it calculates. Over here, what it does, it calculates the ratio between G prime and G. And then if it is almost 1, that is a usual way of saying that it's a bilayer. And when it's trilayer, it usually is more than that. And it can actually identify up to 5 layers of graphene. And then it just says that it is graphite. With respect to the AB stacked or twisted, as of now, it is not. There is no functionality, but this would be a good idea to actually study that if we can. Yeah. Can you explain the diffs tab again? Okay. So in the diffs tab, what it does is it shows the normalized difference between the ideal G versus G prime spectrum of that spectrum. So what it does is it has an ideal G versus G prime version, and it subtracts the current G versus G prime version and then reports those values. The lower the difference is, the higher it is near the monolayer. So that is why it is saying that it is almost a monolayer. Whereas if you consider this to be the difference, so we have already put in these ideal G versus G prime values for monolayer, for bilayer, for trilayer, for 4 layers, and for 5 layers. And then it automatically says that it is graphite. So what it does is it compares the current, the G versus G prime peak, G versus G prime ratio of the raw data or the fitted data to this idealized version, and then shows the difference over here. So that is what this whole diffs tab is about. Is the ratio printed out? Not exactly. No, it is not. It does not print the ratio, but we can definitely add that as a add that feature. Yes. Okay. If there are no questions, I will move to the submit and query tool, which is the main Gr-ResQ or Graphene-ResQ tool, and you can access it using this Gr-ResQ tab in My Tools, or you will have to probably search for it, or you can use the link that was sent previously. And then you launch the tool. So with the Submit tool, there are actually a lot of features that we can use. I can talk about over here, but I will try to speed in the whole process. So the first thing that we wish to do is to submit a recipe. So how does a synthesis recipe normally look like? This was also again sent to you in your tool tutorial. And usually a synthesis recipe contains what the catalyst is, what is the cross-sectional area of the tube that was used during the furnace process, in the furnace, and then what is the base pressure, what is the sample size. And these are basically the experimental parameters. So what you do is you would go ahead and enter all of these values. I would really want to actually enter those values, but in interest of time, I probably won't be able to do that. So let me just enter some values over here. For example, this is a sample surface area of 150 millimeters square. I think the tube diameter was 25 millimeters. You can always go ahead and change these as well, depending on how your instrument is. And then you can say that the tube length was 500 millimeters. And then another thing that we usually wish to know is where the sample was actually inside the tube. And what you can do is the next is that you can add a step. By adding a step, you're actually adding one of these processes: annealing, growing, and cooling, which were discussed in the start of the CVD process. When I was explaining the whole process of CVD. So once you press on annealing, it is going to allow you to enter duration, and you can enter the time that you would want for annealing, or you've used for annealing. And then you can enter furnace temperature. For example, 1000 degrees Celsius is a normal growth temperature for graphene on copper. And then furnace pressure, let's work at atmospheric pressure. And then sample location. This is where we have discussed a lot that actually the sample location matters a lot. And this was also discussed during the workshop yesterday and today. And we usually place it at the center of the sample, center of the tube. And then we flow helium at about 300 standard cubic centimeter per minute, which is again a flow rate of how much gas is flowing. And then we also flow hydrogen during graphene growth on copper. We do not flow argon, and instead we use helium. So you can actually leave this place blank. In annealing process, you don't use any carbon source. So we are not going to write any carbon source flow rate, or we are not cooling because we are actually holding the sample at that temperature. The next thing that you would do is you would add a step. And then you would go ahead and change this annealing into growing. And then, for example, you wish to grow for 10 minutes. And then for 1000 degrees Celsius, again, at 760 torr pressure, which is basically atmospheric pressure, and you're not moving the sample. And you maintain the 300-300 ratio for hydrogen and helium. And now you have a carbon source of methane, and you want to flow 3 SECM of the methane gas. And again, there would be no cooling rate and annealing. We would add the next step as cooling. So let's cool the sample. So again, it would take probably 15 minutes for the temperature to fall from 1000 degrees to 300 degrees. So you would enter the end temperature over here. And then you would enter again the furnace pressure, 250, and then this was again 300. I do not wish to flow hydrogen while I'm cooling, and I don't have argon. I do not wish to flow carbon either, so I'm just going to leave that blank. And then the cooling rate is approximately 53 degrees Celsius per minute. And once this is done, you can actually go ahead and press submit over here. When you press submit, it is going to say that base pressure was missing. So there are some parameters which, if are missing, it will not allow you to actually submit a recipe. So you have to actually enter this value. And this is an important part because these are some important parameters that actually define the graphene growth recipe. And that's why these have been made mandatory. So once you've done this, you can go ahead and click next. It will take you to the properties tab. So for example, if you've already done the growth and you have done Raman analysis on it, you can actually enter that, okay, I have a bilayer graphene that has formed, and then I have about 70% growth coverage. But if you don't have these values, that is totally fine. You need not have actually enter this. And you can just leave it blank. And then you can press next. And then over here, you will upload an SEM image. You can upload a Raman spectroscopy file. It has the same requirements that the SEM image has to be a JPEG file, PNG file, or a TIFF file, while Raman spectroscopy file has to be a text file. You will also have to enter the wavelength that you use to measure Raman spectroscopy. This is because the 2D or a G prime peak is actually a double resonant, it's a resonant peak. And because of that, it can vary depending on laser that has been used. And hence this wavelength is really important. And then I'm not going to upload any images here in interest of time. So I'm just going to go forward, but you can obviously upload a lot of images and there is no limit to that. And then when I click on next, it says it goes to provenance tab, which is the tab over here. So these are the main 5 tabs. I kind of forgot to explain that in the start. But yeah, so we basically follow preparation, properties, then we upload files, and now is the provenance. So in provenance, you're going to talk about what material you're actually growing. This has been created as other because we wish to actually expand this for a lot of other materials. Then you would enter the experiment date, and then you would add the author name. So you can go ahead and enter your name. And if you are actually a member of the group, you will have all of these saved in your computer, so you wouldn't have to actually enter everything. And then, so this author is added over here, and then you can click on next. And you can again check whatever you've entered, and then you can press on submit. Are you sure you want to submit this recipe? Yes. And the recipe is successfully submitted. So once it is actually submitted, it will go to the towards temporary database area where we have to validate this recipe. So once it is validated, only then it will actually be available in our query tab. Another thing that I would like to add is before we were submitting the recipe, it also asks us to connect to Awesome. So Awesome is another tab over here, and you have to make an account on Awesome and then use that username to log in over here. Once you do that, you can automatically connect to the Awesome cloud, and you can request some X group to synthesize graphene for you. Or you can also do it in your own group where you wish that some lab mate synthesizes 2 layers of graphene for you, and you can submit the recipe over there. There is also functionalities to actually connect the tool directly to Awesome, so that everything that has been being processed, and after the whole synthesis recipe is over, it saves all the data and uploads it back to Awesome, and no human interaction is actually required in that as well. And that was basically the submit tool and the Awesome tool. And we have one more tool left, which is the query tool. So if you have any questions on submit, I think you can ask now. How do you make an Awesome account? What is the URL? So Awesome URL is, I am not sure about this, but I think it is this, .illinois.edu. Does the database allow updating the parameters after submission? As of now, no. Once you have submitted the recipe, you will not be able to update the parameters as such. So that is another thing that we should add. Yes, we will be working on that. Thank you. So if there are no questions, we can move to query tool. And So in query, you can basically either search for a recipe for some specific type of graphene that you want, or you can search for recipes for just growth on copper, or you have a number of possibilities to actually filter or sort. So over here, you can search based on the experimental conditions, the preparation, the properties, provenance information. For example, you wish to just search for recipes grown by some specific group. You can actually go ahead and do that. And then you can either search by last name, first name, or institution, and then it's going to ask you to submit to choose from the institution. You can also search based on Raman analysis, where you are entering, I want the weighted G to G peak greater than, for example, I just want something greater than 0, and I'm just going to add that as a filter. So what it does, it actually finds whichever recipes have whichever recipes are actually abiding by this condition that you have stated over here. It will show all those results. So when you click on one of these, it will show you the properties, the conditions, and every other recipe details that were submitted along with this whole experiment recipe. You can also click on SEM and see if it has SEM images. So it has some 6 SEM images, and then you can see the Raman data, if there is any spectrum that has been updated, or if just values have been updated over here. So you can see that these are the G peak and G prime peak, and then the shifts, etc. And then you can also see the recipe over here. So this is very similar to the heat temperature versus time diagram, and you can choose whether you want to just study when carbon was flowing. Since this is the x-axis is the time scale and the y-axis is the carbon source flow rate, you can change it to furnace temperature, for example, and it will show you what was the heat treatment cycle of the whole experiment. So that is what this tab gives you. Provenance tab says who was the actual author. So this was manufactured by Kai-Hao at University of Illinois. And yes, the admin tab is for the group members. So once you've actually queried your recipes, you wish to, for example, plot some input parameter versus an output parameter. So you can, for example, take average carbon flow rate, and then you're plotting it for G prime versus G. So this is the Raman value. But as you can see, there is no direct relation that you can see between the Raman value that has been presented and our average carbon flow rate. But we know that this is actually a case. We know that carbon flow rate affects the number of layers that are being formed. But we cannot exactly see it over here because there are a lot more parameters that are actually affecting the growth conditions. And in order to actually look into those parameters, we have also added another statistical method, which is called TSNE. So what TSNE is, it is a dimensionality reduction technique. What it does is it takes all the input parameters, and then there are about 30 to 35 input parameters that we actually enter when we are submitting a recipe. So it takes all of these input parameters, and when you plot them in a n-dimensional space, you will actually see a trend in them. But if you have 30 to 35 parameters, you're going to have 30-dimensional space, which obviously we cannot visualize. So what TSNE does is it takes this whole 30-dimensionalized space and reduces it to a 2-dimension so that we can actually analyze this using, we can visually analyze this whole process. So over here, you can see that there are 3 things. So one is the feature. So feature is basically the parameters that are present in the query results that have been submitted. So there are 14 parameters that it works on over here. And by support, it means how many of the query results actually have all 14 parameters. When it says that the support is 1, it means that all the recipes that were queried have all these 14 parameters present in that recipe that was submitted. So we can obviously go with that. You can change the minimum support value over here. And then, for example, you choose the 14 parameter. And then, for example, you choose average carbon flow rate. And you go ahead and plot it. So once you come into this section, you have to actually run the TSNE analysis. So it is going to run for you. But you can't see anything as of now. That is also because we have not selected any coloring method. So over here, we can see that there was no relation between average carbon flow rate. But when we go towards maximum temperature or maximum pressure, we can see that all of these are very similar. And for example, it uses helium. What happens in a TSNE plot is that, it takes all these n-dimensional space and converts it into a 2-dimension. So it only maintains the distance between these, the Euclidean distance between these dimensions, and then projects it onto the 2-dimension. So whether the plot is onto the left or right does not matter. But if you see a clustering, that means that there is some kind of relation or correlation between the parameters that we are studying. So over here, we can press on maximum pressure. Okay, maybe I'm not getting anything message right now. So there is a possibility that the query results that I've actually selected have no correlation between them. That is also possible. So according to this whole analysis, this is what we can see as of now, that there is kind of no correlation. It's just present in the dimensional space. So this is another TSNE. This is one of the statistical methods that we can use to analyze the results that were queried. There is another thing that you can do, that you can, for example, sort it based on the weighted G versus G prime, and then find recipes that have either monolayer or bilayer, etc. You can also add more filters. For example, if you wish to have, for example, let's go for preparation, and you wish to have furnace temperature which is greater than 1000 degrees Celsius. So it will then add a filter and then show you only recipes which have the furnace temperature greater than 1000 degrees Celsius. So basically, this is these are the main features of the query tool. So I think this is what the whole tool is about. And I would like to go back and finish up the presentation. If you have any questions on this tool, you can please post them now. How many recipes has the library reached thus far? And do these recipes have all parameters that you have shown or partial sets? So as of now, I think we have around 200 recipes. And do these recipes have all the parameters that you have shown? Yes, most of the recipes have all of these parameters that we are talking about, because we consider them really important and we make a note of it. But there are some recipes that we have. So when we were doing this whole analysis of how many parameters go unreported, we found that we were studying a lot of papers, and those recipes have also been updated. So the tool actually has recipes with missing parameters as well. I am not sure of what percentage is that as of now. Yeah. My query results page is always empty. Maybe you have selected some condition which as of now is not met. For example, if you select experimental conditions, catalyst and palladium, and just add a filter, it should usually show all the recipes, because these have been validated. So since this was not validated, you will not be able to see this recipe, but this was submitted by me today. So this is today's date. So yeah, you will not be able to see that, but apart from that, you should be able to see all of these recipes. Okay, if there are no more questions, I will go back to the presentation mode. So so the whole set of tools as well as the data analysis has everything about Gr-ResQ has been published, and this is the link to the publication. I think we will also share the slides with you later, so you will be able to access that.